We'll now discuss the enzyme catalysis. Now, as you know, the catalysis by enzymes. As you know, that enzymes are biological catalysts. Now, their function is just like any other catalyst, but they're very efficient. And remember that in our body, there are many reactions that don't happen under normal temperature and pressure conditions, but they happen in the temperature of the body, which is just around 98 Fahrenheit. And then you can realize that at a very low temperature, the enzymes very efficiently carry out those reactions. And without enzymes, we won't survive. And in our body, there are thousands of enzymes that are doing catalysis for many important reactions for which we survive. Now, the first model for enzyme catalysis was put forward by Michaelis and Menten, and who provided a very interesting concept of enzyme and how the enzyme actually forms or helps in forming a product from a substrate. So if you consider that there is a substrate, we call it as S, and that substrate is going into product, and in presence of the enzyme, which we write as E, how one can write the kinetic model for this enzyme mediated catalysis, or which is known as enzyme catalysis. Now, what Michaelis and Menten considered is similar like we just talked about. So there is a step where enzyme and substrate binds and unbinds together, and there is a formation of a complex which is known as enzyme substrate complex. This is the intermediate, and that complex actually gives rise to the product. Now, as before, we can think about two rate constant K1 and K minus 1, and K2 for the rate of product formation. And we will also consider the steady state approximation for the enzyme substrate complex. Now, the solution is very easy, but for what Michaelis and Menten came up with is cleverly manipulating the reaction, the amounts of enzyme and the substrate, because you cannot measure them. What you can measure is the initial enzyme concentration, which you had started with, and the initial substrate concentration, which you know. These two things you know. And then what Michaelis and Menten asked is that if we know only these two parameters, how we can write the rate of product formation. That is the entire thing. So given I have these two information, how I can write or how I can express this equation, dp/dt. So we'll follow the usual procedure using steady state approximation of for the intermediate, which is the enzyme substrate complex or the ES complex. Now, this dp/dt is nothing but, it will be K2 into the concentration of this enzyme substrate complex. So we need to know this concentration, and for that we'll use as usual the steady state approach, and that says that dEs dt, which is 0 under steady state approximation, and that is nothing but, so it is forming at a rate K1 into into S. It is decomposing at a rate K minus 1. It is giving back the reactant and the reactants, which are enzyme and substrate, and also it is forming product at a rate like this. So from that you can easily figure out what is the ES. So ES will be nothing but K1 into, or we can actually write it slightly differently before we write the equation for the ES. This is nothing but K1 into E into S minus K minus 1 plus K2 into ES. Now, as I said that we have no idea on the E and the S, otherwise we could have solved it. All we know that E0 and S0. Now, initially, if we start with the initial enzyme concentration as E0, you can always argue that at any time there will be some free enzyme available in the reaction mixture. There will be some enzymes which have formed this enzyme substrate complex. So instead of E, we'll write it as E0 minus ES. That's why I did not eliminate ES at this step or wrote the value of ES and put it back. And similarly for the initial substrate concentration, if that is S0, so at any point there will be some free substrate in the reaction mixture. There will be some enzyme substrate complex in the reaction mixture, plus some substrate has been already converted into the product. Here, once you have the product, the enzyme actually is you regain the enzyme because it's a catalyst. Now from that you can easily figure out what is the we need actually the enzyme as well as the substrate. So at any time the substrate concentration will be nothing but the initial substrate concentration minus ES minus P. So now you can combine these two and see what we are getting. So we'll just replace these values of E and S in this equation to get, or we can write it in the next page because we need to do some approximation. So it will be K1 into E into S. So it will be K1 into E0 minus ES. Let us write it. So it is K1 into E0 minus ES. And then we have the substrate concentration, which is S, and S is nothing but S0 minus ES minus P. Minus P, and that should be, so that should be equal to, or there is another term, it is minus K1 plus K2 into ES, minus K1 plus K2 into ES, that is equal to 0 under the steady state approximation. So now we'll make a further approximation. We know that at any point of time, this enzyme is basically binding to the substrate, but this enzyme substrate concentration is much less than the enzyme concentration itself, because the reason is it's much less than the initial enzyme concentration. The reason is you started with some amount of enzyme, and then only very initially or at any point actually you'll have only few of them are bound to the are present as enzyme substrate complex, because most of them have, if they bind, actually they have formed the product, or they have actually done something else. They have actually gone back to the initial reactants, which are enzyme plus the substrate. So that will be always less than the enzyme concentration, and you usually start with very large excess of the substrate, because you know that enzyme is a catalyst, and you need it a catalyst you need for a very little amount compared with the reactant. So this S0 is pretty high compared to ES, so we can actually ignore the ES term here. So that is assumption number 1. Assumption number 2 is that if you are asking this question that at t equal to 0, what will happen? So at t equal to 0, the amount of the product, that also you can approximate to be nearly equal to 0. So if you if you add these two things, then we can get K1 into E0 minus ES, and this term will be nothing but S0 because we ignored both this term. We can ignore this term also, so it is just times S0 minus K1 plus K2 into ES, that is equal to 0. But this is at the beginning, meaning when t tends to 0, meaning it's the initial time. While this is always true because the substrate concentration is always much larger than the enzyme concentration, initial enzyme concentration, which is of course larger than the enzyme substrate complex, always. So at initial time, which is the second condition, we have this, or we can now eliminate ES or evaluate what is the value of ES. So ES will be nothing but, if you collect the terms, it is K1 plus K2, and then there will be a term which is K1 into S0. So we can write it like this, ES times, it is K1 plus K2 plus K1 into S0, that is equal to K1 into E0 into S0. So ES is nothing but K1 into E0 into S0 divided by K1 S0, or you can just write it as, yeah, that's fine. We can just write K1 S0 at the beginning plus K1 plus K2. So just check once more what are the, it should be K minus 1 plus K2, it should be K minus 1, it should be K minus 1, it is K minus 1. Okay, fine. So the rate of product formation, which is dP dt at t tends to 0, because that's the initial rate, which we call as also V0, which we can write as now, which is nothing but K2 into ES, ES evaluated at t tends to 0, and which is given by this. So I'll have basically K2 into K1 S0, I'm just writing the S0 with K1, and then multiplied by E0 divided by K1 S0 plus K minus 1 plus K2, and we can divide the numerator and the denominator by K1 S0. So you see there is another K1 S0 here. So what we'll get is nothing but K2 into E0 divided by 1 plus K minus 1 plus K2 divided by K1 into 1 by S0. So that we can write in a shorthand form that V0 is nothing but K2 into E0, that we are writing it as Vm. The reason will be clear in a while, and then divided by 1 plus all these combinations we are writing as a constant, which we know, which is known as Michaelis constant. It is named after Leonor Michaelis. It's Michaelis constant into 1 by S0. So if we plot the initial rate, remember V is, it is not V, actually it is V0, which means it is the rate of product formation at a very early time, versus the substrate concentration, and you will see that at a very small substrate concentration, what will happen? So this will be a very large, this is a large number, right? So at a if S0 is very large, so what you will have is that Km by S0 is a very small number that you can actually ignore. So if we plot it in terms of the substrate, initial substrate concentration, and then we'll see that let us just consider at a very high value of the substrate concentration. So if it is a very high value, so then 1 by S0 will be very small number. So we can ignore this Km divided by S0, that term, with respect to 1, and then V0 will be nothing but equal to some velocity of the reaction, which we are calling as, say, Vm. And at a very early, very small substrate concentration, when S0 is very small, then we cannot write it. So so then let us just do it like this. So when S0 is small, then we can write that Km by S0, that is much greater than 1. So what you have is nothing but it will be Vm divided by Km into S0. So V0 will be nothing but Vm divided by Km, and then this S0 goes up. So it is, I see that this Vm by Km, if we consider it to be constant, it is a constant because Vm is nothing but K2 into E0. K2 is a constant, and E0 is initial enzyme concentration, which is also constant. So it's a constant times S0, so which means at early time it will vary linearly with respect to the substrate concentration. So we'll have just a linear slope, and at a very large substrate concentration, when this is very high, so we can write that Km by S0 is much less than 1, which means V0 is nothing but, I can ignore this term compared to 1, it is just equal to Vm. So then it will basically be a constant, which is K2 into E0. Now that's why it says that the initial velocity can have a very maximum velocity, and that's why we wrote it as a Vm. Some textbook, instead of Vm, they write it as Vmax, because it is known as, which is basically K2 times the E0, is sometimes known as the Vmax, and which is nothing but the maximum velocity or the maximum rate. Now what happens is that there are some enzymes in your system, and when you start with a very, very small substrate concentration, then there are more number of enzymes than the substrate. But if you think about that, if you keep on increasing the substrates, so then actually all the enzymes, all the active site of the enzymes will be now occupied by the surface, and there is no free enzyme. So you cannot have a rate which is now dependent on the substrate concentration. Even if you keep on adding the substrate, all the enzymes right now are occupied by the substrate. So you basically saturate your system, and that's exactly what you see here in the following the Michaelis-Menten equation. But always keep in mind that here we are not plotting velocity versus substrate concentration. It is the initial velocity, because we made an assumption where we showed that this product concentration is almost 0. So what you are doing in the experiment is that you are mixing the substrate with the enzyme, with the known concentration of the enzyme. You are basically adding the substrate, and you are measuring the rate at a very early time. And then you change the substrate concentration, again you measure the rate at a very early time. And that way you are measuring, keeping the initial enzyme concentration same. Because you have to keep the K2 into E0 same, otherwise Vmax will also differ if you vary the E0 also. So then you see that it basically gives you a saturation-like behavior. Now in this equation is known as the Michaelis-Menten equation, but you could actually write the equation in a slightly different way, because always you would like to fit any equation in a linear fashion. So you can easily recover the linear equation if you take the reciprocal of this. And that was first shown by two scientists, Lineweaver and Berg, who just took this Michaelis equation and plotted the inverse of V0, so which is 1 over V0. So if you see, if I write it as 1 over V0, it will be on the right hand side, it will be 1 over Vm plus Km by Vm into 1 over S0. So what we'll have is 1 over V0 is 1 over Vmax plus Km by Vm into 1 over S0. So how this plot will look like, if we plot, instead of V0 versus S0, if we plot 1 over V0 versus 1 over S0, of course that will be a linear plot, but let us consider the slope and the intercept. Now think about it, the slope of this reaction, or first let us consider the intercept. If we consider the at what point it cuts the, say, y-axis. Cutting y-axis means actually the x position will be 0, so 1 by S0, that is 0 at that point, so it will cut it at 1 over Vm. So it will be a linear plot because we can see from here. But what about the intercept at the x-axis? So x-axis intercept means actually the y value will be 0, so we can put 0 here, and we can ask what is the value of 1 by S0. So 1 by S0 will be nothing but, we can take this on the left hand side, minus 1 over Vm, and then we can multiply it by Vm into Km, so it will be nothing but 1 over Km with a negative sign. So it just cuts the x-axis at negative 1 over Km. So this is negative 1 over Km. And this plot is known as Lineweaver-Burke plot, and it is often used, and it will be very useful, particularly when you consider the enzyme inhibition. Now, what is enzyme inhibition? Suppose every enzyme has some kind of shape, because enzyme is very particular for a particular substrate, and a very specific substrate can actually get bound to this enzyme, and then you form an enzyme substrate complex. Just like this, and then so this is the equilibrium which we showed, and then this substrate actually forms some different product, and then the enzyme releases the substrate, and we get the free enzyme back, and then the enzyme is ready to bind to another substrate, and that is how it works. Now you can see that for a particular enzyme there is a particular substrate, so it's a kind of known as the lock and key mechanism. So you can see it that there is one key for one particular lock. So the binding of the substrate to the enzyme is very specific. So enzymes are very specific in nature. It will not work on many different molecules. Sometimes it may, but usually enzymes are very specific to a particular molecule or a particular set of molecules. And that molecular shape and the three-dimensional structure determines which enzyme is acting upon this molecule. Now, once we have this situation, once we have very large number of substrate, then there will be no free enzyme in your system, and then you will reach a saturation condition which is here. At a very high enzyme concentration, you have already reached the maximum velocity. Now, sometimes there is another quantity that you would like to measure, that what is the maximum number of enzyme to substrate conversion per minute. What are the number of this thing per minute per unit enzyme concentration? Because if you have more enzyme concentration, then you will have more maximum velocity. So that will be nothing but so what you are asking is basically Vmax by E0. What is the Vmax by E0? And that will be nothing but equal to K2. So this number is known as the turnover number, meaning how many times the enzyme is turning over a substrate into product. It is basically doing this catalytic cycle per unit time, because there is a time already involved here. It's a Vmax, because it's a K2 there, it's a rate constant. So there is a first order rate constant, which means it is how many times it is doing. But we know that it is dependent on the initial enzyme concentration. So we are asking this question per unit enzyme concentration. So if I take 1 molar enzyme, theoretically, or say 1 micromolar, we fix the concentration. Then we ask this question, what is this number? And usually this number, if you take 1 enzyme molecule, this number usually for most of the enzymes varies from 10 to the power 2 to 10 to the power 3, which means it does this substrate to product cycle about say 100 to 1000 per second. But sometimes you can actually go to very high limit, like 10 to the power 6 also. So every 1 microsecond it does a conversion, which means in 1 second it does 10 to the power 6 or 1 million substrate to product conversion. Now it gives you a feeling how enzymes are so efficient, how and why enzymes are so efficient and in converting the substrate, and how basically it has a very efficient rate in the process. Now the next thing we'll just do is that we'll just build up our discussion on this Lineweaver-Burke plot, and we'll discuss how enzyme inhibition happens. By enzyme inhibition, we'll see that if there is some other substrate which actually has some shape, or some other molecule which has the same shape just like the substrate, which we call as an inhibitor, if that actually binds to the enzyme, what will happen to the kinetics of this enzyme? What will happen to this enzyme kinetics, and what will happen if we now plot 1 over V0 versus 1 over S0 in the Lineweaver-Burke sense? So that we'll discuss in the next part.